From third year CSC C section, and my case study topic is construct a direct acyclic graph for a basic block of code and perform register allocation, and showing how common sub expressions are eliminated. And the introduction to direct acyclic graph and register allocation is: a direct acyclic graph (DAG) is a data structure used to represent dependencies between operations in a program. Register allocation is the process of assigning program variables to a limited number of machine registers to optimize performance. Combining these two, direct acyclic graph construction with register allocation helps improve code efficiency by minimizing register spills and redundant computations. And the basic block overview is: here is the diagram which shows the rearranging order of the code. A basic block is a sequence of consecutive statements with a single entry point and a single exit point. It contains no branches or jumps within the block, making it suitable for optimization. Analyzing basic blocks individually simplifies the process of constructing DAGs and performing register allocation. So here is the example code snippet. So consider the following code: a equals to b plus c, d equals to a. Here the expression is f equals to d minus c and g equals to a plus f. This simple code snippet will be used to illustrate the DAG construction and register allocation process. In the step 1, identify operations and dependencies. So break down the code into individual operations and note the data dependencies. For example, variable a depends on b and c, and d depends on a and e. Recognizing these dependencies is essential for building an accurate DAG. And the step 2 is construct the direct acyclic graph. Create nodes for each operation such as addition, multiplication and subtraction. Draw direct edges from operands to their respective operations to illustrate dependencies. The resulting DAG visually represents the order of execution respecting data dependencies. So here is the visual representation of the DAG. The DAG nodes include add node for a equals to b plus c, multiply node for d equals to a, and subnode for f equals to d minus c, and add node for g equals to a plus f. So edges connect nodes based on data flow. For example, b and c to the addition node. Here is the step 3. Determine live ranges of variables. Analyze the DAG to find when each variable is needed during execution. Live ranges indicate the span of instructions during which variables are active. Understanding live ranges is crucial for effective register allocation to avoid spills. So register allocation strategies. The goal is to assign variables to a limited number of registers efficiently. Techniques include graph coloring, linear scan, and priority-based methods. Graph coloring is commonly used with DAGs to minimize register spills by coloring nodes. Applying graph coloring to a DAG. Nodes representing variables are colored such that no two adjacent nodes share the same color. Each color corresponds to a register. If color exceeds available registers, spilling occurs. Optimal coloring reduces the number of register spills, improving execution speed. So here is the one example for graph coloring to a direct acyclic graph. The example of register allocation is: suppose two registers are available, assign A to register R1 and B to R2. Allocate other variables based on live ranges and colors, minimizing spills. adjust assignments if conflicts occur, possibly introducing temporary storage or spills. The main benefits and limitations of this topic is using DAGs and register allocation techniques enhances program performance and resource management. Limitations include increased complexity for large code blocks and the potential need for spilling. Continuous improvements aim to optimize these processes further for modern architectures. And the conclusion and summary of this topic is constructing a DAG helps visualize dependencies and optimize instruction scheduling. So effective register allocation using DAGs reduces spills and improves runtime and efficiency. And these techniques are fundamental in compiler design and contribute to optimized executable code. The references which I take from these information are compilers principle techniques and tools, so which is written by the Aho, Lam, Sethi and Ullman. And the next reference is uh, Muchnik, so advanced compiler design and implementation book. And the third reference is modern compiler implementation in Java, which is written by the Apple. And finally, thank you sir for giving this opportunity.